Good afternoon, first off. Some of you know the work we've been doing here. I've been leading a project in Grays Harbor, studying juvenile habitat use juvenile fish habitat use, largely funded because of salmon, but we've worked with all the fish. And this is sort of very much a side project that we did in 2012 because we were tasked with trying to figure out, okay, in the estuary, what are the areas that are most important for salmon, and what restoration projects should we proceed with? And it became rapidly apparent as I started reading into global warming and paying attention to what's going on, global climate change, it's not warming everywhere, that the elephant in the room that people weren't really talking about was sea level rise, because that's going to undermine a lot of the work that has been done in the last decade. Putting in tide gates or bridges or things like that, you need to start taking this stuff into account. And so we ran the model, the SLAM model, I'll talk about a little bit more later on. And the one thing I'll say at the beginning is this is sort of a first pass. Our question was, what's going to change the fastest and which habitat types are going to disappear most quickly from a salmon perspective. So I think this has a lot of value for other kinds of planning, but as Brad acknowledged, there's a lot of error in the model. So and the resolution at which you run it also generates error. So I'll talk about that more later on. Hopefully we'll have some funding available later on to do it at high resolution. Okay, so a little bit of background here. This is work that you may have seen. It's largely from the Climate Impact Group at University of Washington. And I'm going to summarize just two slides. One is from there and one's from the IPCC on sea level rise. This first slide is showing you the effect of climate change on three different types of river systems in the state of Washington. So the black line up here is the historical pattern, and then there's three different levels, increasing levels of climate effect. And the top, this is the Chehalis, the Yakima, and the Columbia. And so these are three different systems. Here in the Chehalis, it's a rain-dominant system. As the name implies, almost all the precipitation, I'm going to take a drink here, sorry, falls as rain. And so, of course, the rain just comes down the river right away. When you have the opposite effect, you have a snow-dominated system. The upper basin of the Columbia is, in wintertime, mostly snow. And so obviously that comes down later on in the spring as the snow starts to melt. And then you have transient systems are in between. As you can see, the transient system is the one that changed the most. I'm not sure why they chose the Columbia, because all the dams in the Columbia make it kind of a strange system to model these days, but this is the Yakima. The Yakima has some dams as well, but what you see is, historically, we start in October, and it's raining a little bit here, the black line, and then the rainfall increases through the winter, and then drops off very quickly as we approach summer, okay? What's going to happen is, what happens in this section is this is snowpack, right? So it's raining, it's falling as snow, it's held, and then when it melts, you get this big spike, and then it drops down again. What's going to happen as the climate warms in this part of the world is it's not going to fall as snow anymore, it's going to fall as rain. So you're going to have the peak over the middle of winter, and the decline is going to come earlier in the spring, and you're left with a summer that is a lot drier, and the water's going to be a lot warmer, which is a problem for fish. So the good news is the Chehalis, relatively little change, both in the quantity and the timing of the rainfall that's expected. Fish, the problem is really that it's going to get warmer, so in the summertime, the spawning salmon, the runs that come back during the summer are going to have a harder time. But I'm not really going to talk about salmon a whole lot more. This is a figure from the 2007 IPCC report. I feel like I'm blocking half the screen here. And so it's kind of hard to see this at first glance. The continents are gray, okay? And some of the water is blue and some of the water is colored. This is showing us sea level rise. So this is North America. This little circle is us. And the first thing you take away is there's a lot of variation, okay? It's not uniform. Some places are getting a lot of, the redder the color is the greater the sea level rise. So it's different all over, and that's based on ocean currents. But what you also see is this top slide is the 20 years from 1993 to 2003. And you see in the Pacific Northwest, it's pretty much a neutral blue color. We didn't really see a lot of sea level rise. But if you go back a little bit further, from 1955 to 2003, you see that it's actually changed somewhere in this range. So it has happened, but the reason it hasn't been pronounced lately, at least from what I've read, is that the land is actually rising the Olympic Peninsula is rising, and Puget Sound is actually sinking a little bit. And we're kind of right in between that area, so it's risen a little bit, just about keeping balance with the sea level rise. It is expected to increase. That's the prediction. And that's all I know about that.
What's the scale on the bottom?
What's that?
What's the units on that scale on the bottom?
This is centimeters, I believe. And I'm not sure why the scales are different. Oh, this is lat long. Okay, so before I start talking about habitat change, I just want to give you some examples of what we're talking about. And we're going to go from the higher elevations to the lower elevations. This is a picture from the surge plain here in the lower Chehalis River. This is a tidal swamp. It's tidally influenced, but the water is all fresh. If you've been in the surge plain, you know this is exactly what it looks like. It's actually very unique habitat. It's also really important for juvenile salmon. As you move down a little bit, we move into what's called freshwater marsh. And this picture is actually taken about 2 turns up the river. There's a very little bit of salinity influence there, but not a whole lot. Again, there's a tidal input where when the saltwater comes in, it backs the river up. So there's a rise and fall. And this is your sort of classic salt marsh. This is the Elk River Estuary in South Bay. The vegetation is a big giveaway, but this is the salt area. And this is one of the things we expect to see increase. And obviously, as you move down to the lowest elevations, you get into these tidal flats, either mud flats or sand flats. And this is from North Bay. And if you've been up there, it looks like that for a long way all the way around. So the SLAM model that we used was developed by this Warren Pinnacle Consulting Group in Vermont. And they were actually originally paid by EPA to develop this software starting back in the 80s. There's been multiple iterations to map national wildlife refuges. They wanted to know how is sea level rise going to affect these areas. And so they actually did the one here in Grays Harbor. That was the first thing that was done. Way back, I think, in the late 90s. And there's 5 major forces in the model. You have inundation, which is incoming water, erosion, overwash, saturation, and accretion. And accretion is the decomposition of organic matter and or river sediments settling out to build up tidal flats, islands, things like that. So then in 2010, Ducks Unlimited actually ran this SLAM model for the entire Grays Harbor Estuary. And that's actually a nice piece of work. But at that point, they were limited by their data inputs. They were using NED data, national elevation data, which has contours of 20 to 40 feet. It's sort of like what they use for contour maps, for backpacking and stuff. That's a lot of error. And then they had LiDAR data that Brad mentioned, which is much higher resolution, only for the area of the surge plain here. And that was accurate to 10 meters. So when they modeled it out, they ended up using cells and kind of divide the whole estuary up into a grid. And each grid was 30 meters on the side. So that's not very fine resolution. And the basis of the SLAM model is the National Wetlands Inventory, which is a 1981 designation that surveyed pretty much the whole country, the major estuaries. And so the figures I'm going to show you are all sort of related to 1981. That's when the clock starts. Okay, so these pictures are all from the estuary, by the way. So hopefully they're not overly distracting from what we're looking at. So we ran our analysis, and the reason we did it was because we had newly available LiDAR data from the 2012 FEMA did some tsunami concern modeling. They did some overflights gathering LiDAR data. And so they actually have data accurate to 2 meters resolution, which is a big step up. But unfortunately, that's so much data that we couldn't run the model for the entire estuary, because this is a very large estuary. So we ended up having to run it at 5 meters resolution. So the nice part about that is if you're really interested in any particular area, you can go back and run a smaller area at the higher resolution. But it's simply too much for most computers to build. And the other major limitation is that there is no good bathymetry data for the Grays Harbor Estuary. And the only data that's available is from the Navy, from something back in like 1973 or something. And that causes problems largely because, as I'll show you in a second with the plots, once something is overrun with water, you just see it as water, right? You don't know how deep it is. And that's a problem, at least in terms of modeling fish habitat or trying to grow oysters or whatever, because some of that stuff is shallow enough to be really, really useful and be great habitat. And some of it, once it gets past about 6 feet of depth here, where the turbidity is pretty high, that kind of stuff falls off really quickly. And let's see, so we modeled it at 3 different levels of sea level rise. The one I'm going to show you today is the it's 59 centimeters by 2100. And that's what's referred to as the A1B scenario by the IPCC. And that, in their projection, is sort of a middle-of-the-road projection of sea level rise. We also modeled at 2 higher levels because there's increasing concern with glacial retreat and ice sheets melting. That's kind of a conservative estimate, and we didn't want this effort to be immediately useless if it was exceeded. So we also did it at 75 centimeters and at a meter. And as a reminder, a meter is about 39 inches. And then we just calculated it, and Brad showed you the chart, we just calculated the areas that would change. So I'm going to show you through these maps. I realize this is difficult to take it all in just as one full shot. But this is 1981. This is sort of when we started the 0 time. And as you can see, the red is dry land. Here's the mouth of the estuary. Here's the surge plain. We're currently right about there. Gray is mudflat or tidal flat. And then there's a variety of other habitats that are scattered about. This dark green is the swamp that makes up the surge plain. You notice that almost all of that is in the surge plain, all that habitat thing. This light blue here is inland freshwater marsh, and then this different color, light blue, is salt marsh. Okay. So a few things to note here. In 1981, we have, by the way, in case you're not real familiar with the estuary, this is what's North Bay area, this is the surge plain, and this is South Bay. And Aberdeen sits right about there. So you see, obviously, there's a huge amount of tidal flats. And that's one of the things about the Grays Harbor Estuary that's really interesting from a habitat perspective. You also see there's a couple islands, Goose Island here and Sand Island here. And this region right here is called Damon Point. So we're going to kind of roll the clock forward to 2100 under the 59 centimeter increase. And what we get is this. The first change on this large scale you see is we lose all this tidal flat. Okay, the water's going to come up and cover that. Again, that's where we'd really like to have bathymetry data so you know what is the depth of that water. But it's enough to cover both the islands by 2100. So Sand Island and Goose Island are gone. And then the other change that at least jumps out to me immediately is you look at the surge plain. We've gone from a forested swamp to a sort of irregularly flooded transitional marsh area. And that's a different habitat. Some species are going to do better in that habitat. Some species are going to do worse. Unfortunately for salmon, I think it's going to be, that's a negative for salmon because that area, the trees will likely die from the salinity intrusion. And so those sloughs that make the area, well, when there's a big flood event, won't have the trees to anchor them down and they collapse. That's conjecture, but that's one distinct possibility. And so, just my other plug on salmon for this talk, what we're focusing on now this year is trying to get some money to study this region over here, which is, as the sea level comes up, this area of tidal intrusion is going to move upstream. We want to figure out how far upstream and then start planning for restoration opportunities there, planning for stuff like that, so that in 20, 30, 50 years, that area can also function as this current area does. So anyway, that's the big picture. I'm going to show you a couple of close-ups of what it looks like here in the surge plain and what it looks like here. And this is a pretty high elevation gradient, not high is maybe not the right word, but much more elevation gain from here to here than from here to here. Okay, so, and a few of the things that Brad mentioned, the major changes, huge loss in mudflats, 83% of the mudflats go away under this scenario by 2100. 2.4-fold increase in salt marsh, 6-fold increase in a regularly flooded marsh, and a 26-fold increase in traditional marsh. Does somebody have a question? Feel free to jump in if you've got a question. Okay, so on to the surge plain. So here's a close-up view. You see several of the major sloughs, blue slough, preacher slough. This whole area, it doesn't actually show up well, there's sloughs everywhere. So this, right now, this land is Mostly forested swamp, the dark green, and then this is freshwater marsh in the light green. And under this scenario, by 2100, and by the way, in the full report, we step through this in 25-year increments, so you can get a better idea of the timing. One of the things that the people who model this stuff on a global scale say, and I think Stephen mentioned it earlier, is they're fairly confident about the magnitude of sea level rise, but they're not real confident about the timing, especially as you go from one area to another. So something to keep in mind. Anyway, here we see, again, the change I mentioned before, where you can actually see, now you can see all the sloughs that are here. And this area has moved to a sort of a transitional marsh habitat. There's a little bit of inland freshwater marsh here. And then the major effect, 97% decline in forested swampland. And again, this area is a off-channel refugia, high water winter refugia for coho salmon in particular, but all the juvenile salmon. So that's a major loss for salmon. Just going to look briefly at South Bay because it's a different contour. And this is the case that Brad was talking about, where a small change in elevation vertically makes a huge difference horizontally. So we look at this area, you can see most of the area is tidal flat. There's a couple sandbars here. This is the Johns River mouth bar, and this is Whitcomb Flat, and it's kind of out here as well. The light blue is salt marsh. There's a few inland freshwater marsh on the Johns River, and then there's a little bit of forested land on the top. And as we roll forward again, you see a pretty dramatic change where all this is now considered open water. Again, the depth, we don't know really what the depth's going to be. But you also see dramatic changes here. That forested land has now become irregularly flooded marsh. And then we have a huge increase in salt marsh along the boundary here. There's also dikes here, and there's dikes on the Johns River that are constraining some of that horizontal flow. So one of the take-homes here, and in a study that they did on Philippa Bay, there was a study done on the Brandt's goose. I think it was DU that did it. They were worried about losing habitat for Brandt's goose. And again, this whole sea level rise thing is sort of a trade-off. You've got some species are going to do better, some species are going to do worse, and you have to kind of figure out, at some level, you'd like to keep the whole ecosystem intact. That's the approach I would encourage, but there's also some choices to be made. What they found in Willapa is Willapa Bay has a huge amount of dikes. A lot of them aren't right at the water's edge, they're set back. And so as sea level rise fills the bay, the water's going to spread out horizontally, and you actually get this net increase in good habitat for a lot of creatures for 20, 25 years until the water hits the dikes. Then the water starts to go up the dikes, it can't spread anymore, so then you start to lose all the shallow water habitats that fringe the estuary. And then as the whole thing gets deeper, then there's increasing net loss of habitat. So a different consideration, and it's one of the reasons why you don't just want to build a whole bunch of dikes and say, we're not going to give up an inch. I wouldn't want to fight the ocean that much anyway, but at some point you need to let the water flow out and create new habitat. You just need to figure out what you want to save, what's the most important, and hopefully make good decisions about what to do with the rest. And so the next slide I'm going to show you is sort of how you can use some of this information to plan ahead. This is a case, this is Ocosta. So on the south shore, this is the Johns River, this is the Elk River. It's a little dark, it's hard to see the slide, but this is State Route 105, runs along here. This is Ocosta. That's Bottle Beach State Park. And right now the road is diked. So the road is elevated, and there's actually a lot of, it's difficult to see again, but there's some natural creeks here. And this area is at least historically, was all kind of a tidal wetland. But the road has now, in theory, protected this region behind it, except that there's this constant seepage of water. So if you live over there, you know there's been some flooding. There's signs up saying, don't drive down the road, it's flooded. There's also a natural bluff that runs along this front here. You can kind of see the transition from the green, swampy stuff to the dry land. And so there's also 3 tide gates that protect that road and that area. There's a tide gate at the junction with the estuary, there's a tide gate here at the corner, and there's one over here somewhere. And those are leaking, so the state is actually beginning to plan for replacing those. And then, so that's okay, but then you look at sea level rise and you're wondering, okay, how many times do we have to replace those tide gates? How many times do we have to raise the road up in order to keep the water off of it? So we're simply suggesting that with this information now, maybe we can do it a different way. And the solution that I would propose is we actually just move the highway back onto the high ground that's already there. And I realize there's lots of issues with who owns the land, and some of this is forest land. And then you build roads that go down towards the water. So by putting in roads like this and getting rid of this one, you allow the water to flow in. The low-lying areas, you get habitat, and you still give people who live here access to the road behind it. Another possibility is that this area is going to flood quite a bit with sea level rise. And it might actually be worth building this road out across that way. Those aren't my decisions to make. I just put this information out there because hopefully people can use this and save a lot of taxpayer money and do some good work for providing ecosystems at the same time. Another example is to plan ahead for infrastructure. And so that means sewage treatment plants, or where's the fire department located, all that kind of stuff. You have to start thinking now 25, 50 years out, where do you want this stuff to be so it's off the water? And one example we found was this area here. This is the wrecking yard on South Bay. And this is the Charlie Creek, which runs around the wrecking yard, flows up here, and there's another creek over here. And so this is a great example of where this area is liable to be submerged, and you don't want to have all those chemicals coming out of the ground. So it's a good idea to move that, do some kind of a land swap, try to get them into higher land. But I need to point out that there's also all these big ponds from the old Weyerhaeuser site, these, what do you call them? Recirculating ponds. So and that's a whole other thing, I don't know anything about that, but clearly they're already pretty highly diked, but they may need to be reassessed in terms of their location as well. All right. Oh, this is just a close-up of the wrecking yard in Charlie Creek. And you can see the water's already coming by a large, basically 3 sides of it right now. So that area is likely to get submerged as sea level rise comes in. And this is what it looks like from the ground, and we're taking a dead in there sample from fish. To the right, down this little side slope is the highway. So there's actually tons of salmon using that creek. Okay, so to step back a little bit and talk about the uncertainty in the models and where it comes from and then where we can improve it. We've talked about this point now quite a bit, so I'm going to just talk about just a few areas that we can improve. The first is digital elevation modeling. So when you fly over a place with a plane and you're shooting down the laser trying to get your elevation, what happens is you don't get a data point everywhere you shoot down. Particularly in areas with heavy vegetation, like in the search plane, the signal gets scattered and there's not a good return. And so you have a computer model that basically goes through and fills in all the gaps based on where the data points all around are, and it interpolates the data. So there's error associated with that. And the last time I heard that error, the best you could do was about 1 meter with that data. So then you end up, obviously if you're going over a field, you're going to get really perfect data, because you're going to get perfect feedback. But depending on what kind of habitat it is, you have issues with the elevation model. There's also uncertainty, as we discussed at the beginning with the SLAM model. If you run it at a 5-meter grid, which is what we did, you get this result. But if you could run it at a 2-meter grid, you'd get a much finer picture of what's going to happen. And then the final point is that the LiDAR data, which is a big step forward in terms of what we've had versus historically, it's now at about 2 meters resolution. It's very expensive to do LiDAR flights, so I'm told. But I know you can also do better than that. So if you're willing to, when I say you're, the government or whoever is willing to spend the money to have that plane fly over and do finer and finer passes, you get better data. And just, there's a cost to it. And I don't know what it is, but it's more expensive, obviously. Okay, and so before we do questions, this is my email. If you want to shoot me notes, comments, whatever, data requests. And then the full report is here at this webpage. Wildfishconservancy.org, and there's if you go to the project page, you'll get not only this climate change report, but we also have produced a final report for each year based on the juvenile salmon, juvenile fish habitat use. So you can look at that as well. All right, any questions? Be happy to answer, otherwise we can move on.
Yes, so we have shellfish. So on the mud flat, we lose 83% of mud flats there. That, I guess, in my own mind, that's making an assumption that mud flats are pretty flat.
Yeah.
And that a meter rise, it just seems hard for me to envision that a meter rise is something out 83%. We no longer be exposed to flood tide. It's hard for me to
Understood. Part of the problem there is that the accretion rates in Grays Harbor are not very high because of the jetty. We used to get sediment coming in from the Columbia River, particularly in wintertime, that would come in and settle here. And because we have the jetty now, there's actually sort of a net loss of sediment. So those areas aren't rebuilding very well. But I would also say that the mud flats is one of those areas where there's a great deal of uncertainty, and particularly because we don't have the bathymetry data to understand. You know, if you can see where all the little fingers are of the channel, then you can predict better where the overwash is going to occur, and areas are going to scour and stay deeper. And so I would say definitely that the tidal flats is probably our lowest area of resolution. Yeah?
I don't know that much about Grays Harbor, but I do know a lot about Willapa. And I'm assuming that overall that applies pretty much to Willapa. It's very similar as far as the tidal flats and the upland salt marsh. I don't see that, that the change is going to be that radical. Shoreline Master Program is already pretty well protected. Everything that you've shown that would be similar to the Willapa. Our shorelines that come down are steep. We've got fairly steep shorelines that are just outside the salt marshes, maybe just fairly steep hills. And so the 3 feet, the 3-foot rise came in sea level and whatnot. It would probably in most places go maybe 20 feet into the shoreline to expand it. So the expansion of the usable or salt marsh and whatnot, I don't see that that's going to happen. It's pretty well protected already in Willapa, and I don't see the advantage along with the fact that we don't have gradual slopes on our shorelines where you come to the edge of the mud flats and whatnot. You have a 3 or 4, maybe 5-foot bank there, and when you start talking about the concept of utilizing some of this stuff for later on for oyster land and so on and so on, after walking these shorelines for quite a long time. And I was thinking in the same terms 25 years ago of what was going to happen. And I've been involved in a lot of shoreline issues for the industry down there, trying to look ahead to see what needed to be protected in the side rising sea levels. Rising sea levels isn't a new concept. And I just don't see how you're going to, in the last two presentations yours and the one before talked about taking advantage, and there may be an advantage out there to this rising sea levels and whatnot. I don't see this looking at a change.
Well, a couple of things to that, and there's no way to get around 25 years of walking around up there and knowing what you're dealing with. But I would say that in the last 25 years, according to the first plot I showed, it really hasn't changed that much, the sea level rise. And the other thing is that, like the north end of Willapa is sort of like the north side of North Bay. It's pretty steep, drops down to the water. That area is not going to change a whole lot. I think in Willapa where you would see the real changes everywhere there's a creek or a river coming in, the water's going to back way up in those relatively low runouts for the rivers. But I don't know Willapa Bay that well. I mean,
well, it's pretty much the same uniform all the way around Willapa. It's either right now it's protected and whatnot, and then you have an abrupt shift up tree line and going up to the hills. And I don't see any expansion. amount to a great deal. And as far as farming oysters on the peninsula at least, since the rising sea level will probably wipe the peninsula out anyhow, just because of well, that's
yeah, no, I hadn't really thought about it.
That's
low elevation.
a joke. That includes Westport too. And you're going to be farming around a bunch of house foundations.
Not ideal.
Not really what I'm looking for.
No. Yeah.
So on the resolution on LiDAR,
Yeah.
2 feet, that's an elevation, right?
Yeah.
So in
2
order to
meters.
get a refinement of the elevation, you just have to keep reflying it, is that right? Or can that be done with a program to reduce it down to less than 2 feet?
There's no way to reduce it with the program that I'm aware of. You have to just fly it at a higher, just do more passes with the plane to get more data, basically. That's my understanding.
So those LiDAR maps are available?
The LiDAR data is available even for this area through there's a Puget Sound LiDAR Consortium. They have a web page. That's where we got the data. And I should mention Andrew, the guy, my co-author here, is the one who actually ran the model. So if you have technical questions on the model, I'd send you to him. But the data is available to the public. I don't know what form it comes into. Like, I don't know that you can plug, like you can just hit play and it'll give you a map, or you need to plug it into a model like this one and then get a map. I'm not sure how that works. Somebody here might know. No. Okay. Did that take care of your question? Partly. Other questions? All right.
Thank you.
Thank you.